Introduction to IPSec ikev2. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are diving deep into IPSec ikev2, one of the most critical protocols in modern network security. If you have ever wondered how secure VPN connections are established or how enterprise networks protect their data in transit, this presentation will give you a comprehensive understanding. IPSec, which stands for Internet Protocol Security, is a framework of protocols that provides secure communication over IP networks. ikev2, or Internet Key Exchange version 2, is the latest and most robust version of the protocol responsible for establishing and maintaining the security associations in IPSec. What makes ikev2 particularly important is its efficiency and reliability. Unlike its predecessor ikev1, ikev2 requires fewer messages to establish a connection, provides better support for mobile networks, and includes built-in NAT traversal capabilities. It is the protocol of choice for modern VPN implementations, whether you are connecting branch offices, enabling remote workers, or securing cloud communications. Throughout this presentation, I'll walk you through the complete ikev2 process, from the initial handshake to the establishment of child security associations. We'll explore real-world configurations, examine packet captures, and discuss best practices that you can apply in your own networks. By the end, you'll have a solid understanding of how ikev2 protects your data and how to implement it effectively. IPSec Architecture Overview. Let me start by explaining the IPSec architecture and where ikev2 fits into the bigger picture. Think of IPSec as a complete security framework rather than a single protocol. It's like a security suite that provides multiple layers of protection for your network traffic. At the core of IPSec, we have two main protocols: ESP, encapsulating security payload, and authentication header. ESP is what most deployments use because it provides both encryption and authentication. only provides authentication and is rarely used in modern deployments. I like to think of ESP as the armored truck that carries your data. It not only hides what is inside, but also ensures nobody has tampered with it. Now, here's where ikev2 comes in. Before ESP can do its job, we need to establish cryptographic keys and agree on security parameters. That's ikev2's role. It's the negotiator that sets up everything ESP needs to secure your traffic. Without ikev2, you'd have to manually configure keys on every device, which would be a security and operational nightmare. The diagram on the slide shows this relationship clearly. IKE version 2 operates on UDP port 500, and sometimes 4500 for NAT traversal, establishing what we call the IKESA, or Security Association. Once that is done, it negotiates the IPSec SA, which ESP uses to protect your actual data traffic. This separation of control plane, IKE version 2, and data plane, ESP, is a fundamental design principle that makes IPSec both flexible and secure. In cloud environments, this architecture becomes even more important. Whether you are using AWS VPN, Azure VPN Gateway, or Google Cloud VPN, they all rely on this same ikev2/IPSec architecture. Understanding these components helps you troubleshoot issues and optimize your deployments. ikev2 versus ikev1. Evolution and improvements. Now let's talk about why ikev2 was developed and how it improves upon ikev1. If you've worked with IPSec for a while, you might remember the complexities of ikev1. It was functional but had several pain points that ikev2 addresses brilliantly. The most significant improvement is the simplified exchange process. ikev1 had multiple modes: main mode and aggressive mode for phase 1, and quick mode for phase 2. This complexity often led to configuration errors and interoperability issues. ikev2 streamlines this with just 4 messages in the initial exchange. It's elegant and efficient. Let me share a real-world example. In one of my previous projects, we were migrating a global network from ikev1 to ikev2. The ikev1 setup required 9 message exchanges just to establish the initial connection. With ikev2, we cut this down to 4 messages, reducing connection setup time by over 50%. For mobile users on cellular networks, this made a noticeable difference in their VPN connection experience. Another game changer is the built-in NAT traversal support. With ikev1, NAT-T was an afterthought, requiring additional configuration and often causing issues. ikev2 includes NAT detection and traversal in the initial exchange. The protocol automatically detects if NAT is present and switches to UDP port 4500, encapsulating ESP packets in UDP to traverse NAT devices seamlessly. The reliability improvements are equally important. IKE version 2 includes request/response pairs with acknowledgements, making it much more reliable over lossy networks. It also supports MoBike, mobility and multi-homing, allowing connections to survive IP address changes. This is crucial for mobile devices that switch between Wi-Fi and cellular networks. Your VPN connection stays up even as your device moves between networks. IKE version 2 message exchange flow. Let us dive into the heart of IKEv2, the message exchange flow. Understanding this flow is crucial because it is where all the security magic happens. I will walk you through each exchange and explain what is happening behind the scenes. The IKESAINIT exchange is where everything begins. The initiator sends a message containing its supported cryptographic algorithms, a Diffie-Hellman public value, and a random number called a nonce. Think of this as saying, "Hello, here's what I can do, and here's my part of our shared secret." The responder evaluates these proposals, selects matching algorithms, and responds with its own DH value and nonce. At this point, both parties can calculate the same shared secret without ever transmitting it over the network. This is the beauty of Diffie-Hellman key exchange. What is happening under the hood is fascinating. Both devices are performing complex mathematical operations to derive multiple keys from the shared secret. They generate keys for encryption, authentication, and further key derivation. These keys protect all subsequent IKEv2 messages, ensuring that even if someone captures the traffic, they cannot read or modify it. The IKEAUTH exchange is where identity verification happens. This is critical because the first exchange, while encrypted, does not prove who you are talking to. The initiator sends its identity, which could be an IP address, FQDN, or certificate, along with authentication data. If using pre-shared keys, this is a hash computed using the PSK and previous message data. For certificates, it is a digital signature. The responder verifies this authentication and responds with its own identity and authentication data. Finally, the create_child_saw exchange establishes the actual IPSec SA that will protect your data. This includes negotiating encryption algorithms for ESP, defining traffic selectors what traffic to protect, and generating new keys specifically for the data channel. The beauty of IKEv2 is that this can happen multiple times, creating multiple IPSec SAs for different traffic types, all protected by the same IKE-SA. Security Associations SA explained. Security associations are fundamental to understanding IPSec, but they are often misunderstood. Let me demystify them for you. Think of an SA as a security contract between two devices. It defines exactly how they will protect their communication. What encryption to use, which authentication algorithm, what keys to apply, and which traffic to protect. In IKE version 2, we work with two types of SAs. The IKE SA is like the master agreement. It protects the control channel where all negotiations happen. Once established, it typically lasts for hours or even days. The IPSec SAs, or child SAs, are the worker agreements. They protect your actual data traffic and are usually shorter-lived, getting rekeyed more frequently for security. Each SA is uniquely identified by a Security Parameter Index, SPI, in your logs and packet captures. You will see these SPIs everywhere. They are like tracking numbers that tell each device which SA to use for processing packets. The initiator and responder each choose their own SPI values, so you will always see pairs of SPIs for bidirectional communication. Here's something that trips up many engineers. SAs are unidirectional. For bidirectional communication, you need two SAs, one for each direction. This might seem redundant, but it provides better security and flexibility. Each direction can have different security parameters, if needed, though in practice, they're usually symmetric. The table on the slide shows typical SA parameters. Notice how comprehensive they are, from encryption algorithms and key lengths to lifetime values and anti-replay windows. When troubleshooting IPSec, checking SA parameters is often the first step. Mismatched parameters are one of the most common causes of connection failures. Modern implementations like StrongSwan and Cisco ASA provide detailed SA information that helps quickly identify such mismatches. ikev2 Packet Structure Deep Dive. Now, let us examine the actual structure of ikev2 packets. Understanding packet structure is invaluable when you are troubleshooting connections or analyzing security. I will show you what these packets look like on the wire and how to interpret them. Every ikev2 packet starts with a 28-byte header. The first 8 bytes are the initiator's SPI, followed by 8 bytes for the responder's SPI in the very first packet. IKSA init. The responder's SPI is all zeros because it hasn't been assigned yet. This is normal and expected. The next byte indicates the payload type, defining what kind of data follows the header. The version field is crucial. It is split into major and minor versions, with IKE version 2 being major version 2, minor version 0. If you see version mismatches in your logs, the connection will fail immediately. The exchange type field tells you which phase of negotiation you are in. 34 for IKESA init, 35 for IKEauth, and so on. The flags field is particularly interesting. Each bit has a meaning. The initiator bit indicates who started the exchange. The response bit distinguishes requests from responses. The version bit is used for version negotiation. During troubleshooting, these flags help you understand the packet flow and identify issues like missing responses or incorrect message ordering. Following the header, you have a chain of payloads. Each payload has its own header indicating the next payload type, creating a linked list structure. Common payloads include SA, Security Association, KE, Key Exchange, NI/NR, nonces, and Notify for status messages. When analyzing packet captures, I always look for Notify payloads first. They often contain error messages that explain exactly why a connection failed. The entire packet after the IKESA init exchange is encrypted and authenticated. This means you can't see the actual payload contents in Wireshark unless you have the encryption keys. However, you can still gather valuable information from the header and packet flow patterns. Cryptographic algorithms and cipher suites. Choosing the right cryptographic algorithms is critical for both security and performance. Let me guide you through the current best practices and explain why certain algorithms are preferred over others. For encryption, AES remains the gold standard. AES 256 GCM is my go-to recommendation for most deployments. It provides authenticated encryption, meaning it handles both confidentiality and integrity in one operation. This is more efficient than older modes like CBC, which required a separate HMAC operation. In my performance tests, AES-256 GCM consistently outperforms AES-256 CBC with SHA-256 by 30 to 40% on modern hardware with AES-NI support. However, not all devices support GCM mode. For compatibility with older equipment, AES-256 CBC with SHA-256 or SHA-384 is a solid fallback. Just be aware that CBC mode is vulnerable to certain attacks if not implemented correctly, though ikev2's built-in protections mitigate most of these concerns. For integrity algorithms, the landscape has evolved significantly. SHA-1 is now considered weak and should be avoided. SHA-256 is the current minimum standard, with SHA-384 and SHA-512 providing additional security margin. When using GCM mode, you do not need a separate integrity algorithm, since GCM provides its own authentication. The Diffie-Hellman groups deserve special attention. Groups 14, 2048-bit MODP, 19, 256-bit ECP, and 20, 384-bit ECP, are the current recommendations. The elliptic curve groups, 19 and 20, provide equivalent security to much larger MODP groups while being more efficient. For example, Group 19 provides security comparable to a 3072-bit MODP group but with much faster computation. Here's a pro tip. Always configure multiple proposals in order of preference. This provides fallback options and helps with interoperability. Your strongest algorithms should be first, followed by progressively more compatible options. This way, you get the best security possible while maintaining broad compatibility. Authentication methods in ikev2. Authentication is where we verify that we are talking to the right peer. ikev2 supports several authentication methods, each with its own use cases and trade-offs. Let me walk you through each option and when to use them. Pre-shared keys, PSK, are the simplest method and still widely used. Despite their simplicity, PSKs can be secure if implemented correctly. The key is using long, random PSKs, at least 32 characters of random data. I've seen too many deployments using weak PSKs like Company 123. These can be cracked in minutes. For automated deployments, I recommend generating PSKs programmatically using a cryptographically secure random number generator. Certificate-based authentication is the gold standard for larger deployments. It provides strong authentication and scales well. The initiator proves its ID entity by signing data with its private key, which the responder verifies using the certificate. The certificate contains the public key and is itself signed by a certificate authority CA that both peers trust. EAP, standing for Extensible Authentication Protocol, opens up a world of possibilities. It allows integration with existing authentication infrastructure, like RADIUS servers, Active Directory, or even multi-factor authentication systems. EAP-TLS uses certificates within the EAP framework, while EAP-MSCHAPB2 can work with username/password combinations. This flexibility makes EAP popular for remote access VPNs where you need to authenticate individual users rather than devices. The authentication process in ikev2 is elegant. During the IK-auth exchange, each peer computes an auth payload by signing a hash of previous messages. This proves not only that they possess the correct credentials but also that they participated in the key exchange. It prevents replay attacks and ensures perfect forward secrecy. In cloud environments, certificate-based authentication is increasingly important. Cloud providers like AWS and Azure use certificates for VPN connections, allowing automated certificate rotation and centralized management. Understanding how to properly deploy and manage certificates is becoming essential for cloud network engineers. Traffic selectors and policy configuration. Traffic selectors are how we tell IPSec exactly which traffic to protect. Think of them as filters that determine which packets get encrypted and which ones do not. Getting traffic selectors right is crucial for a functional IPSec deployment. A traffic selector consists of IP address ranges, protocol numbers, and port ranges. For example, you might protect all traffic from 10.1.0.0/24 to 10.2.0.0/24, or just HTTPS traffic on port 443. The flexibility is powerful but can also lead to complexity. In the ikev2 exchange, both peers propose their traffic selectors, and ikev2 negotiates a common subset that both can accept. Here is where many deployments run into issues: traffic selector mismatches. If the initiator proposes 10.1.0.0/24 to 10.2.0.0/24, but the responder expects 10.1.0.0/16 to 10.2.0.0/16, then the negotiation will fail. The error messages can be cryptic, often simply stating no proposal chosen. When troubleshooting, always verify that traffic selectors match on both sides. Policy-based VPNs use traffic selectors directly to determine what to encrypt. When a packet matches a selector, it's sent through the tunnel. Route-based VPNs work differently. They use a virtual tunnel interface, and routing determines what goes through the tunnel. However, even route-based VPNs use traffic selectors under the hood, often set to quad 0/0, any traffic. In complex networks, you might need multiple traffic selectors. ikev2 handles this elegantly by allowing multiple child SAs, each with its own selectors. This lets you apply different security policies to different traffic types. For instance, you might use stronger encryption for sensitive database traffic while using faster algorithms for bulk data transfers. The configuration example on the slide shows a typical scenario. Notice how we specify both local and remote subnets, creating a bidirectional policy. Modern implementations like StrongSwan can automatically derive the reverse direction, but it is good practice to be explicit in your configuration. NAT traversal in ikev2. NAT traversal is one of ikev2's most elegant features. If you've ever struggled with IPSec behind NAT devices, you'll appreciate how seamlessly ikev2 handles this challenge. Let me explain the problem and how ikev2 solves it. The issue with NAT and IPSec is that ESP packets do not have port numbers. NAT devices need port numbers to track connections and modify packets correctly. Without ports, NAT devices cannot handle ESP traffic properly. Additionally, IPSec's integrity checking detects the IP address changes that NAT performs. It sees these changes as tampering, causing packets to be dropped. ikev2's solution is brilliant in its simplicity. During the IKESAINIT exchange, both peers include NAT detection payloads. These contain hashes of the IP addresses and ports they see. By comparing what they sent with what the peer received, they can detect if NAT is present. If NAT is detected, they automatically switch from UDP port 500 to port 4500 and enable UDP encapsulation for ESP packets. The UDP encapsulation adds an 8-byte UDP header to each ESP packet. This gives NAT devices the port numbers they need to function correctly. The overhead is minimal, just 8 bytes per packet, but it solves the NAT problem completely. In my experience, the performance impact is negligible, usually less than 1% in throughput tests. There is one caveat to watch for. Some firewalls and NAT devices have session timeouts. If no traffic flows for a period, often 30 to 120 seconds, they might close the NAT mapping. ikev2 handles this with NAT keep alives, small packets sent periodically to keep the NAT mapping active. Most implementations send these every 20 to 30 seconds when NAT is detected. The configuration for NAT-T is usually automatic, but you can tune parameters like keep alive intervals. In environments with aggressive NAT timeouts, reducing the keep alive interval can improve stability. Just remember that each keep alive consumes bandwidth, so find the right balance for your network. Dead peer detection (DPD). Dead peer detection is a critical feature that keeps your VPN connections reliable. Without DPD, a peer could disappear, maybe due to a crash, network failure, or power loss, and the other side wouldn't know. It would keep sending traffic into a black hole. Let me show you how DPD prevents this problem. DPD works on a simple principle. If you haven't heard from your peer in a while, send a message to check if they are still there. If they do not respond after several attempts, assume they are dead and clean up the connection. This frees resources and allows for faster recovery when the peer comes back online. ikev2 implements DPD through informational exchanges. These are lightweight messages that serve multiple purposes, such as carrying status notifications, deleting SAs, or simply acting as keep-alives. For DPD, we send an empty informational request. If the peer is alive, it responds with an informational response. Simple but effective. The timing parameters are crucial. The DPD delay determines how long to wait before sending a DPD probe. I typically set this to 30 seconds for site-to-site VPNs and 10 seconds for remote access VPNs. The DPD timeout defines how long to wait for a response. Usually 120 seconds is reasonable. After 3 to 5 failed attempts, the SA is cleared. Here is a real-world optimization. ikev2's DPD is on demand by default. It only sends probes when there is outbound traffic but no recent inbound traffic. This is more efficient than ikev1's periodic DPD. If your peer is actively sending traffic, there is no need for DPD probes. The traffic itself proves the peer is alive. In cloud environments, DPD becomes even more important. Cloud infrastructure can be ephemeral. Instances might be terminated, replaced, or migrated. Aggressive DPD settings help detect these changes quickly and trigger reconnection. For AWS VPN connections, I recommend matching your DPD settings to AWS's defaults. 30-second delay, 120-second timeout, for optimal interoperability. IKE version 2 configuration examples. Let's get practical with some real configuration examples. I'll show you how to configure ikev2 on different platforms and explain the key parameters. These examples represent common deployment scenarios you'll encounter in production networks. Starting with StrongSwan, which is my favorite open source implementation. The configuration is clean and logical. In the IPSec.conference file, we define connections with their parameters. The IKE parameter specifies the IKE proposals, which are algorithms for the IKE SA. The ESP parameter defines proposals for the child SA. Notice how we can specify multiple proposals separated by commas, allowing for algorithm negotiation. The authentication section is where you specify credentials. For PSK, you put the key in IPSec.secrets. For certificates, you reference the certificate and private key files. The auto parameter controls connection behavior. Start initiates on startup, root initiates on demand when traffic matches, and add just loads the configuration without initiating. For Cisco iOS, the configuration is more verbose but follows a similar logic. You create an ikev2 proposal that lists your algorithms, then group proposals into a policy. The crypto ikev2 keyring holds your authentication credentials. The ikev2 profile ties everything together and references your peer identity. Finally, the crypto map applies the configuration to an interface. The tunnel protection method on Cisco is particularly elegant. Instead of complex crypto maps, you apply IPSec directly to a tunnel interface. This makes the configuration cleaner and enables dynamic routing over the VPN. It is my preferred method for site-to-site VPNs on Cisco devices. One tip for all platforms: always include detailed descriptions and comments in your configurations. Document why specific algorithms were chosen, what the peer represents, and any special requirements. Your future self or colleague will thank you when troubleshooting at 3 a.m. Troubleshooting ikev2 connections. Troubleshooting ikev2 doesn't have to be a mystery. Over the years, I've developed a systematic approach that quickly identifies most issues. Let me share my troubleshooting methodology and the most common problems you'll encounter. Always start with the basics. Can the peers reach each other? A simple ping test often reveals routing or firewall issues. Remember that ikev2 uses UDP port 500 and 4500 for NAT. Many connection failures are simply due to these ports being blocked. Use TCP dump or Wireshark to verify packets are flowing in both directions. Next, check your logs. ikev2 implementations provide detailed debug information. On StrongSwan, Swan CTL log shows real-time negotiation. On Cisco, Debug Crypto ikev2 reveals the entire exchange. Look for proposal mismatches, authentication failures, or certificate validation errors. The error messages might seem cryptic at first, but they usually point directly to the problem. Proposal mismatches are incredibly common. The initiator might propose AES 256 SHA 256 MODP 2048, but the responder only accepts AES 128 SHA 1 MODP 1024. The solution is to ensure at least one proposal matches on both sides. I always configure multiple proposals to improve interoperability. Start with the strongest algorithms and include more compatible options as fallbacks. Authentication failures come in many forms. For PSK, verify the keys match exactly. Even a single character difference can cause failure. For certificates, check the entire chain. Is the certificate expired? Is the CA certificate installed? Does the certificate subject match the peer's ID? Certificate issues often show as authentication failed without more detail, so systematic checking is essential. Traffic selector mismatches are subtle but frustrating. The tunnel might establish successfully, but no traffic flows. Check that your selectors encompass the actual traffic. Use packet captures to see what traffic is attempting to use the tunnel. Sometimes the issue is as simple as a typo in an IP address or subnet mask. ikev2 in cloud environments. Cloud environments have become the primary deployment scenario for many ikev2 implementations. Each major cloud provider has its own approach to VPN services, but they all build on the ikev2 foundation we have been discussing. Let me share insights from deploying ikev2 across AWS, Azure, and Google Cloud. AWS Virtual Private Gateway, VGW, is perhaps the most straightforward. It supports ikev2 with a good selection of algorithms. AWS automatically handles redundancy by providing 2 tunnel endpoints for each VPN connection. The key to success with AWS is understanding their specific requirements. They expect certain DPD timers, prefer specific algorithms, and have particular expectations about traffic selectors. Always download the configuration templates AWS provides and adapt them to your device. Azure VPN Gateway offers more flexibility but requires more configuration. You can choose between policy-based and route-based VPNs, with route-based being more powerful. Azure's implementation supports a wide range of algorithms and even allows custom IPSec policies. One unique aspect is Azure's support for active-active configurations, providing better redundancy than traditional active-passive setups. Google Cloud VPN has evolved significantly. Their Cloud VPN now supports high-availability configurations with automatic failover. Google's implementation is particularly strong in its BGP integration, making it excellent for dynamic routing scenarios. They also provide comprehensive metrics and logging, which helps tremendously with troubleshooting. Across all providers, there are common considerations. First, understand the pricing model. You pay for both the VPN gateway hours and data transfer. Second, consider regional availability. Not all VPN features are available in all regions. Third, plan for scalability. Each provider has limits on bandwidth, number of tunnels, and connections per gateway. My recommendation is to use infrastructure as code for cloud VPN deployments. Tools like Terraform or CloudFormation make it easy to deploy consistent configurations across environments. They also make disaster recovery straightforward. If a region fails, you can quickly deploy the same configuration elsewhere. Performance optimization. Optimizing ikev2 performance requires understanding both the protocol mechanics and your hardware capabilities. Let me share techniques that can dramatically improve your VPN throughput and reduce latency. Hardware acceleration is your first consideration. Modern CPS include AES-NI instructions that accelerate AES encryption by 3 to 10 times. Ensure your kernel and ikev2 implementation support these instructions. On Linux, cat/proc/cpu info pipe grep AES confirms AES-NI availability. For Strong Swan, the OpenSSL plugin automatically uses AES-NI when available. The performance difference is dramatic. I have seen throughput jump from 200 megabits per second to 2 gigabits per second just by enabling hardware acceleration. Algorithm selection significantly impacts performance. AES-128 GCM typically provides the best performance on modern hardware while maintaining strong security. It's about 30% faster than AES-256 GCM and significantly faster than CBC modes. For integrity, avoid separate algorithms when using GCM mode. The authenticated encryption handles both confidentiality and integrity efficiently. Packet size optimization often goes overlooked. IPSec adds overhead, typically 54 to 73 bytes depending on algorithms and encapsulation. This can cause fragmentation if your original packets are near the MTU limit. Set your tunnel MTU to accommodate this overhead, usually 1436 bytes for a 1500 byte physical MTU. MSS clamping on TCP connections prevents fragmentation at the source. For high throughput scenarios, consider multiple child SAs. Modern multi-core systems can process multiple SAs in parallel. By creating multiple child SAs for the same traffic selectors, you can distribute load across CPU cores. This technique is particularly effective for 10+ gigabits per second connections. Some implementations like Strong Swan support this natively with the install routes equal operator no option and custom routing. Finally, tune your kernel parameters. Increase network buffer sizes, enable TCP offloading where appropriate, and optimize interrupt handling. On Linux, settings like net.core.rmem_max and net.core.wmem_max should be increased for high bandwidth VPNs. CPU affinity settings can also help by dedicating specific cores to crypto operations. Security best practices. Security is paramount when deploying ikev2. While the protocol itself is robust, implementation weaknesses can undermine your security posture. Let me share best practices developed from years of security assessments and penetration testing. First and foremost, use strong authentication. For PSKs, generate random keys of at least 32 characters. Never use dictionary words or predictable patterns. I recommend using a password manager or scripting the generation. For example, OpenSSL RAND base 6432 generates a strong PSK. Store these keys securely. They're essentially the keys to your kingdom. Certificate-based authentication is superior for most deployments. Use certificates with at least 2048-bit RSA keys or 256-bit ECC keys. Implement proper certificate lifecycle management, regular rotation, revocation checking, and secure storage of private keys. Hardware security modules, HSMIS, or TPM chips provide the best protection for private keys. Perfect forward secrecy, PFS, is non-negotiable in modern deployments. Always use DH groups in your child SA negotiations, not just the IKESA. This ensures that compromising one key does not compromise past or future communications. Yes, it adds computational overhead, but the security benefit far outweighs the performance cost. Limit your algorithm proposals to strong options only. Remove weak algorithms like DES, 3DES, MD5, and SHA1 from your configurations. Even if you do not intend to use them, their presence allows downgrade attacks. Regular security audits should verify that only approved algorithms are configured. Finally, implement comprehensive logging and monitoring. Log all IKE negotiations, authentication attempts, and SA establishments. Monitor for anomalies like repeated authentication failures, unusual peer addresses, or unexpected proposal changes. These often indicate attack attempts. Tools like fail2ban can automatically block repeated failed attempts, adding another layer of defense. ikev2 extensions in future. ikev2 continues to evolve with extensions that add new capabilities. Understanding these extensions helps you leverage advanced features and prepare for future developments. Let me highlight the most important extensions and where the protocol is heading. MoByte, which stands for Mobility and Multihoming, is perhaps the most impactful extension. It allows ikev2 connections to survive IP address changes seamlessly. This is revolutionary for mobile devices that switch between Wi-Fi and cellular networks. The VPN connection stays active as users move, providing a seamless experience. In my testing, MoByte handovers complete in under 2 seconds, often unnoticed by users. The redirect mechanism allows load balancing and maintenance without disruption. A VPN gateway can redirect clients to another gateway transparently. This is invaluable for large deployments where you need to distribute load or perform maintenance. The client receives a redirect notification and reconnects to the new gateway automatically. Fragmentation support addresses a common issue with large certificates or many proposals. IKE packets can exceed MTU limits, causing connectivity problems. The fragmentation extension splits large IKE messages into smaller fragments, ensuring reliable delivery even with restrictive firewalls or small MTUs. Post-quantum cryptography is the next frontier. Current public key algorithms will be vulnerable to quantum computers. The IETF is working on integrating post-quantum algorithms into ikev2. Hybrid modes will allow using both classical and post-quantum algorithms during transition. While quantum computers aren't an immediate threat, planning for this transition is crucial for long-term security. Looking ahead, we're seeing integration with modern authentication systems like OAuth and SAML. Zero Trust network architectures are driving requirements for continuous authentication and microsegmentation. ikev2 will likely evolve to support these paradigms while maintaining backward compatibility. The protocol's extensible design positions it well for these future requirements. Real-world deployment scenarios. Let's examine real-world deployment scenarios where ikev2 shines. These examples come from actual implementations I have designed and deployed, showcasing different use cases and architectural patterns. The multi-cloud scenario is increasingly common. Here, we are connecting AWS VPCs, Azure VNets, and on-premises data centers in a full mesh topology. ikev2's certificate-based authentication scales beautifully here. We use a private CA to issue certificates for each endpoint, enabling automated certificate rotation. BGP runs over the ikev2 tunnels for dynamic routing, adapting to topology changes automatically. The key is standardizing your ikev2 parameters across all platforms to ensure interoperability. Remote access for a global workforce presents different challenges. We deployed ikev2 with EAPTLS authentication, integrating with Active Directory through Radius. Users authenticate with certificates stored on smart cards, providing strong two-factor authentication. Mobike ensures connections survive network transitions. We geo-distribute VPN gateways, using anycast IPs and redirect mechanisms to connect users to their nearest gateway automatically. The site-to-site scenario shown connects branch offices with varying security requirements. Critical sites use a ES256 GCM with 4096-bit certificates. Less sensitive locations use a ES128 GCM for better performance on limited hardware. Traffic selectors segregate different types of traffic, such as voice, data, and management, into separate child SAs with appropriate QoS markings. For disaster recovery, we implemented an active-passive setup with sub-second failover. The primary gateway advertises more specific routes via BGP when it fails. DPD detects the failure within 30 seconds, and the backup gateway begins advertising routes. Using route-based VPNs with identical configurations on both gateways ensures seamless failover. Each scenario teaches valuable lessons. Document everything meticulously. Test failure scenarios regularly. Monitor performance continuously. And always have a rollback plan. ikev2 is robust, but complex deployments require careful planning and ongoing management. Advanced topics and considerations. Let's delve into advanced topics that separate competent ikev2 deployments from exceptional ones. These considerations often make the difference between a VPN that merely works and one that excels in performance, reliability, and security. Session resumption is an underutilized feature that dramatically improves user experience. Instead of performing full ikev2 negotiation for every connection, clients can resume previous sessions using stored keys. This reduces connection time from seconds to milliseconds. It is particularly valuable for mobile users who frequently disconnect and reconnect. The implementation requires careful key management to balance convenience with security. High availability deserves special attention. Active-active configurations provide better resource utilization than active-passive setups. Using anycast IPs, multiple gateways can share the same address, with routing protocols directing traffic to the nearest gateway. State synchronization between gateways ensures sessions survive gateway failures. Technologies like Cluster XL or proprietary solutions achieve millisecond failover times. Quality of service integration ensures critical traffic receives appropriate treatment. ikev2 can copy DSCP markings from inner packets to outer ESP packets, preserving QoS through the tunnel. Some implementations support per-child SA QoS policies, allowing different treatment for different traffic types. This is crucial for voice and video applications that require low latency and jitter. Quantum-safe deployments are beginning to appear. While full post-quantum algorithms are not standardized yet, hybrid approaches provide future-proofing. These use classical algorithms alongside experimental post-quantum algorithms. Even if the post-quantum algorithm proves weak, the classical algorithm maintains security. Google's experiments with New Hope in Chrome demonstrate this approach. IPv6 considerations become increasingly important. ikev2 handles IPv6 naturally, but dual-stack deployments introduce complexity. Should you tunnel IPv4 over IPv6? IPv6 over IPv4? Both over both? The answer depends on your network architecture. Generally, native transport for each protocol performs best, using separate child SAs for IPv4 and IPv6 traffic. Conclusion and key takeaways. As we conclude our deep dive into ikev2, let me summarize the key concepts and provide you with actionable takeaways. We've covered a lot of ground, from the protocol basics to advanced deployment scenarios. ikev2 represents a significant evolution in VPN technology. Its streamlined negotiation, built-in NAT traversal, and extensibility make it the protocol of choice for modern VPN deployments. Whether you're securing cloud connections, enabling remote workers, or connecting branch offices, ikev2 provides the foundation for secure, reliable communications. Remember these critical points. First, security starts with strong authentication and modern algorithms. Never compromise on cryptographic strength for compatibility. Second, proper planning prevents poor performance. To do this, understand your traffic patterns, size your gateways appropriately, and optimize configurations for your specific use case. Third, monitoring and logging are not optional. In fact, they are essential for security and troubleshooting. Looking forward, stay informed about protocol developments, post-quantum cryptography, enhanced authentication methods, and integration with zero-trust architectures will shape IKE version 2's future. Participating in communities, reading IETF drafts, and testing new features keeps your skills current. For your next steps, I recommend setting up a lab environment to experiment with different configurations. Try integrating ikev2 with your authentication infrastructure. Test failure scenarios to understand recovery behavior. Most importantly, document your implementations thoroughly. Your future self will thank you. ikev2 might seem complex initially, but it is elegant in its design. Master the fundamentals we have covered, and you will be well equipped to design, deploy, and troubleshoot ikev2 in any environment. Whether you are working with traditional networks or cutting-edge cloud architectures, these skills remain invaluable. Thank you for your attendance. Please consider subscribing to the channel.